Welcome back. Today we'll cover functions and their graphs. If you remember, the independent variable includes all the inputs or the x values. And then after we plug it in, we'll get an output or a dependent variable, often using the variable y. Now all those values that we plugged in represent the domain. And all the values that come out represent the range. Whenever we determine a relationship is a function, we often use function notation. And it's shorthand to identify that that is a function. And in words, we say f of x. Whenever we have more than one function, we'll use different letters like g of x and h of x. Now, a relationship is a function when every x has one y. So in this table, we actually can look at some examples of the times during the day. And if you notice, each time of the day matches up with one temperature that day. So if we had something maybe at 1 p.m. matching up with two different temperatures, well, that wouldn't make sense because at 1 p.m. it can only be one temperature in one location. So if this happens where an x value has two y values, then that would not be a function. Another way to make sure a relation is a function is to look at its graph. So if a graph has one y for every x, then it's a function, meaning it passes the vertical line test. All right, let's get into some examples. So if we have the equation x squared plus y squared equals 8, we have to decide if that's a function. You could do a couple things. You could plug in numbers and see what you get, or you can graph it. And this graph is the equation of a circle. And we know that a circle would not pass the vertical line test because there are 2 points at some of the values for x. Now let's evaluate the function given different values for x. So when we plug in 2 for x, we'll get 10 minus 3 times 2 squared. That equals 10 minus 3 times 4, or 10 minus 12, which equals negative 2. For f of negative 4, we plug in negative 4 wherever we see x. So that equals 10 minus 3 times negative 4 squared, which is 3 times 16, 10 minus 48, which equals negative 38. And for the final example, we're going to plug in x plus h. So this will equal 10 minus 3 times the quantity x plus h squared. So that'll equal 10 minus 3 times x squared plus 2xh plus h squared, which equals 10 minus 3x squared minus 6xh minus 3h squared. And we'll write that in standard form. So that equals negative 3x squared minus 6xh minus 3h squared plus 10. For our next example, we'll look at a batter. And here we have Derek Jeter, who hits a baseball at a point 3 feet above the ground at a velocity of 100 feet per second and an angle of 45 degrees. The path of the baseball is given by the function f of x equals negative 0.0032 x squared plus x plus 3, where f of x is the height of the baseball in feet, and x is the horizontal distance from home plate. Now we have to decide and figure out if Derek Jeter's hit that looks like a downward parabola, or opening downward parabola, will clear a fence that's 300 feet away. And this fence is 10 feet high. So if we plug in 300 into the function, and this value, this y value, is greater than 10, then we know that this baseball will clear that fence. So when I plug in 300 for x in the equation, this will simplify into negative 288, and the y value will equal 15. And remember, the fence is only 10 feet high, so yes, this baseball will definitely clear the fence. Now let's consider piecewise functions. And it's exactly that. They're pieces of functions. So for this function, it's actually broken into two. So wherever the value for x is less than 0, we're going to use the first line. And wherever the x value is greater than or equal to 0, we'll use the second function. So right here, we have f of negative 2, and negative 2 is less than 0. So we're going to plug negative 2 into the first equation. So we get negative 8 minus 4. So f of negative 2 equals negative 12. Now for the next one, 0, remember 0 is going to be in the second equation. So f of 0 will be 3 times 0 plus 1. So that'll equal just 1. And for the next value, for 2, we're going to plug 2 in to the next or the second equation because it's greater than 0. So f of 2 equals 3 times 2 plus 1. So that's just going to be 7. The difference quotient, which you're actually going to use a lot in calculus. So here we have a function, f of x, and if you notice, this function is increasing, but it's not a constant line. It's increasing, and it's positive here, but as you go further to the right, the line is getting steeper and steeper. So when we talk about the difference quotient, we're actually looking at 2 points here. And say we don't know exactly, but we know that there's a value for x, and we plug that in, we're going to get that point x and f of x, which is our y. And then say we had another point, which was h units away. So if that point was h units away, the coordinate for this point would be x plus h and f of x plus h. Now we could find the change between these 2 points with this secant line, and we can actually use, it's pretty much just like slope. We could find the change in the y and then the change in the x just by finding the difference. The change in the y would be f of x plus h minus this f of x. And the change in the x, well, that would just be x plus h minus x, which equals h. So if we wanted to write that in slope formula form, the difference quotient can be written as f of x plus h minus f of x over h. Now the difference quotient will be different for every function. Now let's consider the difference quotient for this quadratic. We're going to plug in x plus h into the equation, so we get x plus h squared minus 2 times x plus h plus 7. That can simplify, let's make this a little bit bigger, into x squared plus 2xh plus h squared minus 2x minus 2h plus 7. Now I'm going to plug it into the difference quotient. So it'll be the f of x plus h, which is this whole expression here. So x squared plus 2xh plus h squared minus 2x minus 2h plus 7. And then subtract f of x. So minus x squared plus 2x minus 7 all over h. Now you'll notice that things cancel. The x squareds, the 2x, and the 7. And we're left with things that will cancel out with the h. So when I'm going to write this first so it's really clear. So we have 2xh plus h squared minus 2h all over h. And then I'm going to cancel out the h's. So this is going to cancel, and we'll be left with 2x plus h minus 2. But remember, we canceled out the h's, so we have to make sure we say h does not equal 0. Cubic. To find the DQ, we're going to plug in x plus h into the original function. So we get x plus h cubed plus 2 times x plus h. If you remember Pascal's triangle, we can actually use that shortcut to expand the polynomial. So this will equal x cubed plus 3x squared h plus 3xh squared plus h cubed plus 2x plus 2h. Now we're going to plug that in for our x plus h. So let's write this out. X cubed plus 3x squared h plus 3xh squared plus h cubed plus 2x plus 2h. And we're going to subtract f of x. So minus x cubed minus 2x all over h. Okay, we're going to have some things cancel here. The x cubes and the 2x. And we're left with 3x squared h plus 3xh squared plus h cubed plus 2h all over h. And we could simplify that to 3x squared plus 3xh plus h squared plus 2, and remember h cannot equal 0. For this example of the DQ, we have a little bit of a trickier problem because there's a fraction. So remember, we're still going to plug in x plus h in for x, for h of x plus h. So when I plug that in, I'll get 3x plus 3h over x plus h minus 7. And then I'm going to subtract the original function, which is 3x over x minus 7 all over h. Now this is where it gets tricky because I actually have to multiply by the LCD. So when I look at the first fraction, I'm going to have to multiply that by x minus 7 over x minus 7, and I'll multiply the second fraction by x plus h minus 7 over x plus h minus 7. Okay, so when I distribute, just don't forget to FOIL for the first fraction. So for the first fraction, we have 3x squared plus 3xh minus 21x minus 21xh. Or just h, sorry, here you go. And then I'm going to subtract the second function here. So that's going to become minus 3x squared minus 3xh plus 21x. And then remember, we have this complex fraction, so the denominator for that was x minus 7 over x plus h minus 7. Whenever we have something with divided by h, that's the same as multiplying by the reciprocal. And we can write that as 1 over h, so that h goes in the denominator. All right, now we have some things that are going to cancel. So let me just mark them off. So we have 3x squared, 3xh, and 21x. So when we simplify this, I know it gets a little confusing. I'm going to draw a little line here. In the numerator, we're going to have negative 21h left in the top over h times x minus 7 times x plus h minus 7. Now the only thing here that's going to reduce is the h. So our final answer will be negative 21 over x minus 7 times x plus h minus 7, where h cannot equal 0. Now let's consider parts of a graph, particularly looking at a function's domain, range, if it's a function, and its zeros. Okay, so the first part is the domain. So in this function, we're actually going to look at all the values to the left and to the right. Remember, the domain includes all the values for x. So when I look at this graph, it goes to the left as far as negative 1. And it goes to the right with an open circle to 5. So that means in the domain we'll include negative 1, but we won't include 5. For the range, we're looking at the lowest y value and the highest y value. So the lowest is negative 3, and then it goes up to positive 3. And it includes both values, so we'll use brackets for both. Now on this graph, it's asking what is f of 2. That means we're plugging in 2 for x, so f of 2 will be negative 3, which is the y-coordinate. We can decide and determine if this is a function using the vertical line test, and it never touches more than 1 point. So this is definitely a yes. It passes the vertical line test. Now the zeros, also known as the roots or the x-intercepts, is wherever the function touches the x-axis. So we have two values here where x equals 1 and x equals 4. And you could also put those as the coordinates 1, 0, 4, 0, which are the x-intercepts. Now let's consider this graph looking at some intervals. So remember, the positive intervals is when the function has a positive y value. So we're looking at y values that are positive. So let me just draw a line here. So it looks like the boundaries would be those zeros. So from here, from negative 1 to 1, not including 1, that function is above the x-axis. And then again over here, after 4 and up to 5. So we're not going to include 4 because that's when it was a 0. And remember, 5 was not included in the domain. So those are the values of x when the y value is positive. Now let's look at when the y value is negative. So it's pretty much in between these two zeros. So it's only going to be negative between the x values 1 and 4. To determine what kind of function we have, we actually first can describe it as increasing, decreasing, or constant. Now, an increasing function could be a linear function with a positive slope. It could be a cubic function. But you can notice wherever you go, as when you continue to the right or towards positive infinity on the x, the y values also increase towards positive infinity. Versus a decreasing function. If it's a linear or maybe a cubic with a negative coefficient, as you progress, as you go to the right in positive infinity for the x values, all the y values will go down towards negative infinity. If a function is constant, it's always a horizontal line. And so no matter how far you go to the right or towards positive infinity for the x values, you're always going to have the same y value. Now let's consider relative max and min. Now, when we looked at quadratics, a maximum would be like the top of the hill. We use the word relative because it's not just for quadratics, but say we have a function that's a quartic or a cubic. Okay, so if we have a function like this, it has relative maximums right there. And I'm going to just continue this function just so that we could see a minimum. Down here. So in between those values of x, we have a relative minimum where there's a low value for the y and a relative maximum or local max where the y value is higher than those other y values. So whenever we look at relative maxes and mins, they're inflection points. They're points where the graph changes. If you notice, if this was a roller coaster, you would be going up and then going down and decreasing, right? And then you get to the minimum here and then you increase again. So between these relative extrema or inflection points, we can actually have different intervals where the function is increasing, decreasing, and constant. But at those extrema, at these functions, relative max and mins, well, you can kind of say it's constant, but only for a brief moment. It wouldn't be an interval, right? It's just for a very brief moment where you have a break at the top of the roller coaster or at the very bottom, but you'll have a longer interval, a longer time, either going up the roller coaster or going down. So whenever we describe these intervals, we use the x values to help us figure out where those intervals are, and we use parentheses because they don't include the extrema. So let's look at this function. That's a cubic. If we want to determine the relative maxes and mins, well, you can see the top of the roller coaster is here. So I'm going to say the relative max, that coordinate would be -1, 2, and the relative min would be down here, +1, -2. Okay, now those are going to be our really key points here. This 1 for x and this -1 where we have the max. So when we look at this function, it's increasing. This roller coaster is increasing. It's going up from -infinity until you get to -1. And then it goes down until you get to the minimum, the relative min. So there's going to be another interval where it's increasing again. From this point, from the minimum down here, where x equals 1, and it's going to keep going to positive infinity. Now you notice that we only use the x values to describe these intervals. Okay, it's kind of confusing because the y tells us if we're going up and down, you need both to figure out if it's increasing or decreasing. But when we're describing the intervals, we only use the x values. Now let's look at the decreasing intervals. So the decreasing, where this roller coaster is probably the most fun, would only be between those values of x when the slope is decreasing or negative. So this decreasing interval would be between the values -1 and 1. Now there's no point in here or no values that have horizontal lines. So there's no constant intervals. Now you might argue that at this point, at the top of the roller coaster and the bottom, it's constant. And it's constant, but there's no slope to be found there, right? We would need 2 points. So it doesn't continue on for very long. So those are called the extrema, they're inflection points. Now let's go back to the difference quotient and the rate of change. So if we're going to find the average rate of change, we would have to actually consider 2 points. So another way to do this is to say, well, we have one point at A and another point at B. And so this point at A, if I plug that into the function, I'll get f of A. And if I plug B into the function, I'll get f of B. And if I wanted to find the average rate of change, or the slope, I would subtract the x's and the y's, right? So this would be the change in the y over the change in the x. So it'd be f of x of 2, or f of b, minus f of x sub 1, or in this picture is f of a. So whenever we're trying to find the slope or the average change, we have to make sure we have those 2 points. Otherwise we get an expression or a difference quotient. So for this one, we're actually going to consider this parabola, and we're just going to find those values where x equals -1 and x equals 3, and determine the rate of change between those 2 points. And for the next problem, we'll consider 2 other points, 0 and 1, and see what happens between those 2 points. So before we can actually find the rate of change, we actually have to find the y values. So f of -1 in this function would be -1 squared minus 2 times -1. So that's just 1 plus 2, so that's 3. And then we have f of 3, so that's going to be 3 squared minus 2 times 3. So that's 9 minus 6, so that's 3. So when we consider that, the average rate of change, or the slope, well, it's going to be the difference in the y's over the difference of the x's. So it's just going to be 0. Okay, but we know that this is not a constant function. We know that the slope would not be 0 all the time, but between those 2 points, it's 0. For the next one, from 0 to 1, I'm going to plug in 0 into the function, which will just be 0. And then when I plug in 1, that'll just be 1 squared minus 2 times 1. So that's going to be -1. So when I find the slope, it's going to be -1 minus 0 over 1 minus 0. So -1 over 1 is just -1. So this is another point. We have a quadratic, and I want to emphasize a quadratic does not have a constant slope. So between these 2 points, the average rate of change is 0, and between these 2 points, the average rate of change is -1. And we try not to say slope unless we're talking about a line. But if you can tell, we're still using a slope formula to find the average rate of change. Now over here, we want to find the distance in feet of a moving car from a stoplight from t is 0 seconds to 5 seconds. So same thing, we're going to plug in 0 into each. Right, so 0, well, I'll just plug it in, but s of 0 would be 30 times 0 to the 3/4. Well, we know 0 to the 3/4 is just 0, and 0 times 30 would just be 0. S of 5 would be 30 times 5 to the 3/4. Now this means that we're cubing 5, so that's 125, and then we're going to take the fourth root, or 125 raised to the 1/4, which is going to be a decimal, and it's about 3.3437. So I'm going to multiply that by 30, so that's going to be approximately 100.311. I'll make that. So if we want to find this, the average speed from those two, from that time, we know it's not going to be constant because the car is going to speed up, it's going to take a while and then probably cap a little bit. So if we wanted to find the average rate of change, it's going to be the distance from 5 seconds, so 100 minus, or 100.31 minus 0, which is 100.311, over 5 minus 0. So it's really just going to be that number divided by 5. So this car is moving at a speed of 20 feet per second. And whenever we give a rate, we want to make sure we get the units. Let's consider functions and determine if they're even, odd, or neither. So let's first define an even function. An even function is a function where when you plug in a value for x with negative x, its opposite, you'll get the same value for y. So if you look at the graph, if I plug in a value here for x, I get, something like 3. And then I plug in a value over here, that same value, but it's opposite, I'll also get the same y value. Whereas an odd function is a little different, where we plug in an x into a function and we get y, but if we plug in its opposite, we'll get a negative y. So both the x coordinate and the y coordinate become the opposite. Now, graphically, an even function is symmetric, means that I could fold it in half on the y-axis and it'll perfectly match. Whereas an odd function, it kind of looks like a rotation instead of a symmetry, but we say it's symmetric about the origin. So if I turn this 180 degrees, it'll look the same on the other side. Okay, now let's consider these functions and just determine if they're even, odd, or neither with the test. So we're going to plug in a negative x. So for the first one, if I plug in negative x, I'll get negative x quantity squared minus negative x quantity to the 4th. Now if we know if we raise something to the squared power, it's going to become positive. And if we raise something to the 4th power, it'll also become positive. So what happens is we get the same exact y value as we did for f of x. So that means that this function is even. For the next one, when we plug in a negative value for x, 2 times negative x cubed plus 1, well, we know that this will become negative, so that's negative 2x cubed. And I'm just going to put this and have the negative distribute, and then plus 1. Well, if you notice, this is 2x plus 1, but this next one is negative 2x plus 1. They are not the same. So if they're not the same, and they're not opposites, that function is neither even or odd. Now let's look at the next one. So this will be negative x to the 5th minus 2 times negative x cubed plus negative x. Well, all of these powers are odd. So this will become negative. This becomes positive, and this will be negative. So if you notice, looking at the original function, that's x to the fifth minus 2x cubed plus x, versus this one is negative x to the fifth plus 2x cubed minus. So every term is switched. It's the opposite. So if everything is opposite, it means that that y value is going to be the negative or value or the opposite. So that means that this function is odd. Now let's go to this example. When we plug in a negative x, we get 2 minus negative x to the 6th minus negative x to the 8th. Again, we're having even degrees here. So this will equal 2 minus x to the 6th minus x to the 8th. And it'll still look exactly the same as the original. So that one will be even. Now let's move on to k of x. For this one, you can kind of notice there's some telltale signs. We have a constant over here, right? So as soon as we know that things are starting to change, we know that it'll be neither, because this doesn't change. So if I plug in a negative x, this will be negative x to the fifth minus 2 negative x to the fourth plus negative x minus 2. To simplify, the evens become positive. So this will stay the same here, 2x to the fourth, and this will become negative x minus 2. So looking at the signs, this is positive, negative, positive, negative. This becomes negative, negative. It's not all becoming opposites, and they're not all the same. So this one will be neither, because it's neither even nor odd. They all have to change and become the opposite, or they all have to stay the same to stay even. Now for the last one, we have p of negative x here. So that's negative x to the 9th plus 3 times negative x to the 5th minus negative x cubed plus negative x. So this will be negative x to the 9th, negative 3x to the 5th, plus x cubed minus x. And looking at the signs, it's positive, positive, negative, positive, negative, negative, positive, negative. Everything is the opposite here, so this function is odd. Now let's go to one more thing with functions. And right here for these two functions, we're actually going to consider and try to find the height between these two functions. So the functions that are shown is this y equals 3, and then this graph y equals 4x minus x squared. So if we're going to find this difference or this height, we'd have to subtract the two terms. So it'll be the top minus the bottom. So h here will be the top, which is 3, minus the bottom. And I could distribute that negative. And then if we're going to write that in standard form, it would be x squared minus 4x plus 3. Now let's look over here. Again, this function up here is shown with the equation 4x minus x squared. So that'll be our top. And we can subtract the bottom, which is the 2x. So minus 2x. Now we have to combine like terms. So this is negative, that'll be positive 2x. So our h will equal negative x squared plus 2x. Now let's look over here, and we're going to consider the length. But instead of subtracting the top minus bottom, we're going to subtract the right minus the left. So this length will be 2 minus the cube root of y. For this one on 86, this equation right here is 2 over y, and this vertical line is x equals 0. So the length will just be the left, which is 2 minus y, minus 0, but that'll just be 2 over y. It's important for these graphs as well, since we're looking at them in their visual. We want the domains for these graphs are restricted. So I'm also going to just include the restricted domain. So for here, for 85, this was from 0 to 2, and this graph was from 0 to 1.